We're now going to talk about normal forms. And these are normal forms for autonomous vector fields. So time independent autonomous vector fields. Near equilibria. And you could use the usual method of, if you do have a non-autonomous vector field, you could transform it into an autonomous vector field, but then you won't have equilibria because the time direction is always moving forward. You could also do normal forms for things other than equilibria, but we're just going to start with equilibria. So just like before, we'll first do the theory for vector fields, and then we'll do the theory for maps. So just to give you a basic idea of what a normal form is, it's a coordinate transformation. It's a nonlinear coordinate transformation of your phase space that simplifies the nonlinear terms. And I'll give us a 1D example. I guess before I do that, why do we want to do this? Part of it is you want to find out if you have two vector fields and they may have a different formula. If they have the same normal form, normal here means standard. You're basically trying to do a coordinate transformation that puts the system into a standard nonlinear form. And then if you could see if two different nonlinear vector fields have the same standard nonlinear form, then they are topologically equivalent. So this helps us determine categories of topological equivalence between systems. And why do we care about that? Here is I've got a nice figure of some kind of topologically equivalent thing. Oh, it won't work. I'll just show the figure. So on the left, in the X1 and X2 phase space, and we've drawn, you can see a couple of equilibrium points. There's an unstable saddle in white, and then there's a black point, which is also unstable. Things are spiraling out. There seems to be a periodic orbit there. And on the right, in the Y phase space, we've got, well, basically the same thing. It's just distorted. In fact, what I literally did is take the image on the left, that phase space, and then use some like Photoshop distortion. But since you could transform one into the other without poking holes, they are topologically equivalent, meaning they'll have the same properties. The equilibrium points will have the same local properties in terms of being a saddle or being, in this case, a source. And there's also a periodic orbit in each. So if we could put these two systems in the same standard form, at least what their vector field looks like, then we could determine equivalence. So these two are topologically equivalent because you could transform them one to the other. So if you've solved for the dynamics for one of them, then you know the dynamics for all of the others. And seeking topological equivalence between systems is a way of basically solving a system. If you have a system that you're interested in, and you could demonstrate it is topologically equivalent to something solved 30 years ago, then you could just use that solution from 30 years ago. As a personal example, I've used it to design a controller for a system. where we were having a hard time sort of tweaking some parameters to find a controller that worked. But then we found there was a topologically equivalent system. It wasn't obvious at first that it was topologically equivalent, but someone had already solved the control parameters for that. So we were able to see how our system deformed into that one, find out what the parameters were, and then deform back. So this is a sort of a larger effort to determine topological equivalence between systems. But let me give a 1D example, and then we'll go through the theory as it's discussed in Wiggins.
So a normal form is basically just a canonical example of a system of, like, the canonical example of the set of vector fields that are all homeomorphic to each other?
Yes, diffeomorphic.
Diffeomorphic, okay.
Yeah. Yes, another way that it's put is that Jordan canonical form is to the linear transformation as the normal form is to the nonlinear transformation. It puts it in its best, simplest representative. All right, so a 1D motivation. This comes from, there's the chapter 13 of Verhulst. It's pretty good, which you can look at. So suppose we have an ODE, and this is just in one dimension. So X is in R, okay. And X dot is, it's got a linear term, and then it's got higher order terms. We got this quadratic term, cubic term, and maybe so on. And we'll specify that lambda is not 0. And we're also going to be, considering a small neighborhood. Near the origin, which you'll notice the origin is the equilibrium point for this system. So we'll be assuming that X is small in whatever we do. Now, let's say we want to simplify the dynamics. So this right-hand side is just too complicated. We'd like to transform our variables to simplify the dynamics. That means simplify these right-hand side terms. And we'll use a near identity change of variables to do this. So what do I mean? So we'll be transforming from X into Y, where we'll pick a form, the transformation. We'll write it as X equals Y. So that's where it's near identity, plus something that's quadratic in Y, plus something that's cubic in Y, and so on. So what we're gonna do is, and we could take this out to any order we want. We want to pick alpha 2 and alpha 3 to simplify the right-hand side of the X dot equation. But now it'll be in terms of Y dot. So we want to simplify the resulting ODE for Y. So we're going to substitute this change of variables into the original ODE up here. And what do we get? We get X dot equals, we can pull out an overall Y dot 1 plus. So right now I'm just doing the chain rule and applying it to the transformation to get taking the time derivative. And we'll get this for how X dot and Y dot are related. And now we'll substitute in the equation up above, which was the right-hand side of the ODE. So this would be lambda, but now instead of x, we're going to write y plus alpha 2 y squared, and so on. That's the first term, plus a2 times x squared, which is now y plus alpha 2 y squared, and so on, squared, plus a3, and now it's x cubed. So we've got y plus alpha 2 y squared, and so on, to the cube. Now collect the terms. Collecting terms, we get, this is lambda y plus, and now we'll collect all the terms that are quadratic in y, lambda alpha 2 plus a2 plus, and now we'll collect all the terms that are multiplying y cubed. This is lambda alpha 3 plus 2a2 alpha 2 plus a3, and so on. So we've got y dot times this thing, maybe we'll put it in square brackets up here, equals this down here. And now we'll, we want to write something that's, you know, y dot equals some stuff on the right-hand side. How will we do that? Well, we'll use a Taylor series expansion that hopefully you've seen. It's whenever you've got 1 plus something small, alpha, and since x is small, you know, anything multiplying y or y squared and so on is also small. If you take the inverse of that, then this is equal to 1 minus epsilon plus things of order squared in epsilon. And this is for epsilon small. So in this case, these terms up here are epsilon. So that allows us to write y dot equals, now it's 1 minus 2 alpha 2 y minus 3 alpha 3 y squared times lambda y plus lambda alpha 2 plus a2 y squared, and so on. Multiply it out, what will you get? The leading order term is going to be lambda y. So it's like just like the leading order term for the x dot equation. And then you'll have the term that's second order in y. And then the term that's third order in y. And so on. So, okay, our original goal was to simplify the ODE for y. And I said we could do that by picking alpha 2 and alpha 3 appropriately. So if we wanted to simplify, well, the biggest simplification would be just to have this coefficient of the first nonlinear term be 0. So if we want this to equal 0, then we can pick alpha 2 is a2 over lambda. And now you know why lambda had to be non-zero. Otherwise, this would be undefined. Okay, so we've simplified that, and we've got what alpha 2 needs to be. We could plug in that here for alpha 2, and we could get rid of this cubic term. And this goes, you know, if you want that to be 0, then you could solve for what alpha 3 has to be make this 0. So we get this. It's a lambda squared. And you could keep on doing this. So then what do we end up with? We end up with, doing a nonlinear transformation, we've now got the y equation looking linear. And we've only computed it through fourth order, but we can continue this. So in the language of Verhulst, we've normalized the ODE. What does that mean? Well, we've shown that even though this may have looked complicated originally up here, oh, x dot equals, oh boy, there's some nonlinear things there. And remember, we're assuming x is small. So very close to the origin, the dynamics of that nonlinear equation for x are equivalent to this completely linear equation for y. And maybe it's useful to think of a picture. So we've got our x space, and here's the origin. And we'll plot, you know, what does the x vector look like? I guess, you know, the sign of these arrows depends on if lambda is positive or negative. But we took this that may have had some nonlinearity to it, but we did a nonlinear mapping, or let's say nonlinear change of coordinates. To make it look linear. When I say make it look linear, well, that means it's topologically equivalent to a linear system. So in the y variables, this thing really is just linear. And if you want, it's as if we've taken, it's like we've done a remeshing of x in order to make y dot look linear. So that's the motivation. There is more to this theory, and it definitely gets more complicated in 2 dimensions or more. But the idea is, you know, having a center manifold feed into this. For center manifolds, you often have on the center manifold, the dynamics reduced to the center manifold are typically nonlinear. The nonlinear terms are important and they matter. But you want to know, is there an equivalence class that this system belongs to that's already been worked out? Or in other words, how do I best simplify the nonlinear terms to see what the dynamics could be? And often some of those nonlinear terms will depend on parameters, and then that then feeds into bifurcation theory. So just with this 1D motivation out of the way, we're now going to dive into the theory as Wiggins has it.
A question regarding this example.
Yeah.
So you make the assumption at the beginning that the right-hand side of the differential equation of motion is a polynomial. Is
Yes.
that just for motivation purposes, or are you assuming that all nonlinear things can be written as a polynomial? So do you need to, how does that work?
Since I'm looking at the origin is an equilibrium point, then in the neighborhood of the origin, you can always write the right-hand side as a polynomial.
I see. So you're basically just kind of taking a Taylor expansion or something equivalent of the function at the equilibrium point, regardless of whether or not that function originally had a polynomial form.
That's right.
Okay.
That's right. Yeah, so it's key that we're doing this near an equilibrium point so that it did go to 0. If we had like a 1 over x dot equals 1 over x, well, that blows up at x equals 0. We don't have an equilibrium. All right. Good question. So now this is chapter 19 of Wiggins. 2003 book, and looking at section 19.1. So this is normal forms for autonomous vector fields near equilibria. We have to go through some steps first. Our original ODE is, let's say, W dot equals G W. So G is our vector field. We're assuming we've got it's n-dimensional, autonomous, and that there's an equilibrium point. Not at the origin, but somewhere. There's an equilibrium point at W naught. Oops. So what does that mean? So that means G of W naught, the vector field vanishes there. So we'll be able to do Taylor series expansion about it. So we're going to have a first transform the equilibrium point to the origin. And we'll use V to describe that. So in the V variables, V equals 0 is the equilibrium point. Right, so V is, so Rn. And what are the equations for V? Well, V dot will be, so V dot is going to be W dot minus W naught dot, but that's just a constant, so that goes away. So we'll have this, and we're going to write this as a function H of V. That just makes life easier. So H of V, it's not the Hamiltonian, we're just running out of symbols. H of V is just defined to be G of V plus W naught. Okay, so now that we've got the ODE in this form, where the origin is an equilibrium point, now we're going to write this right-hand side where we split off the linear part of the vector field. So we will write the linear part. It's going to be the Jacobian of H evaluated at the equilibrium point. So, right, this is linear. And then we'll call all the terms that are second order and higher, call it H bar of V. So these are purely nonlinear. So what is H bar V? It's just H, V, and then subtract off the linear part. Okay, so this is definitely going to be of order 2 and higher. Then so the first step in simplifying the nonlinear terms is you first simplify the linear terms. So simplifying the linear terms, right, we get the DH evaluated at the origin it's a constant matrix. So we will simplify it, right? We get the eigenvalues and the generalized eigenvectors, BH0, to construct a transformation to a linear transformation to Jordan canonical form. All right, so we're going to do a transform. We went from W to V, now we're going from V to X. And we define it as B equals some transformation matrix T. Right, made up, the columns will be chosen as the generalized eigenvectors. So that X dot is T inverse DH0T times X plus, and then the nonlinear parts, we deal with them just like we have been dealing with them when we did center manifold theory. So it's T inverse H bar of T X. This matrix T inverse, the Jacobian at the origin times T, is the most simplified representation of the linear dynamics, the Jordan canonical form, which instead of using capital lambda, I'm going to follow the notation of the book, and this is called J. So it's not the canonical symplectic matrix, it's the Jordan canonical form. And then this part over here, we'll refer to this as f of x. So this defines f of x, this defines j. So the equation that we will work with is, we have simplified the linear terms completely. And that is the first step. So we've simplified, just what I said, the linear terms as much as possible. Now we'll do the same for the nonlinear terms. You might think, oh, this is a hopeless endeavor, but it's not. It's not. So what we do next is we Taylor expand f of x, basically splitting off everything that's second order, everything that's third order, and so on, so that we could treat them in sequence. So we've got terms that are purely second order, terms that are purely third order, terms that are purely fourth order, and so on. What do I mean by that? It's a homogeneous polynomial of order 2 in the x variables. Right, what does it mean? X is, we typically think of it as, it's going to be made up of an n tuple, x1 to xn. And then F3, same thing, homogeneous polynomial of order 3 in the x variables, and so on. So we can, I guess, summarize that. Fix are terms of order I. So now x dot is jx plus f2x plus f3x, and so on. So we've already simplified the linear terms. Now we'll simplify the second order terms. And this will introduce a lot of the theory. We basically just set up our ODE so it's in the right form for us to now begin the systematic approach to constructing the nonlinear coordinate transformation. So we'll simplify the second order terms. And we'll do that. So up above, what did we do to simplify the linear terms? We introduced a linear transformation. Now we're going to introduce a coordinate transformation to simplify the second order terms. And this is from X to Y, where kind of like in the motivation, we're writing the X variables or the original variables equals Y. So it's a near identity transformation plus this little h2y. This is a second order homogeneous polynomial in Y. And we don't know what h2 is. h2 is currently unknown. We're going to solve for it. Just like in the motivating example, we had coefficients of second order and third order terms, and then we solved for them. Right now, we don't know because this is a vector valued polynomial. So now we'll use the chain rule and just take the time derivative of x. So take d by dt, x dot, and then take the time derivative of the right-hand side. We get y dot plus, well, now we get, so Jacobian of h2 times y dot. Pull out an overall y dot, and what do we get? This big one is the n by n identity plus dh2y. Is that it? Yeah, that's it. No, I guess we need a, no, we got it. So this is the n by n identity. And this is the Jacobian of the unknown h2. So you might be wondering what kind of thing is h2, or what do we mean second order homogeneous polynomials? So I'll just give you an example of terms of h2 for the case of a two-dimensional vector field. And this is what, so x1, x2, I'm just sort of writing out this equation up here, but writing out all of the terms. So that's the identity part. And then we have a bunch of unknowns. A1 times, and here's a second order part of the polynomial. Y squared, but in the first slot, and then plus A2, Y1, Y2 in the first slot, plus A3, Y2 squared in that first slot. Hopefully you get the idea. And then now we have to do, there's three more. It's the same second order terms, but in the second slot. So plus B1, plus B2, Y1, Y2 in the second slot. That's it. And then you could just solve for the A's and B's. We're going to do this a different way. And what we need to say something about here is that the space of vector valued homogeneous polynomials of degree 2 on Rn is a vector space with basis elements. So what I've written here are the 6 basis elements of the second order polynomials for the case n equals 2. And there's coefficients. So the key thing is it's a vector space. It's a linear space, and we could reduce the problem of finding the coordinate transformation. Even though it's a nonlinear coordinate transformation, we could turn it into a linear problem. Something that's equivalent to AX equals B So let's set that up. So I should say, basically going to say that again. The space of vector valued homogeneous polynomials of order 2. I guess it's sometimes said of degree 2, and it doesn't matter. On Rn. So we'll say H2. We'll write it as capital H2. Is a vector space with basis elements. And here is basis element P J. Yeah, I think it's capital P J. So here's one of the basis elements. It is, hold on. Y1 raised to the M1 power, Y2 raised to the M2 power, and so on, times Yn raised to the Mn power times Si, where, what is, a few things going on here. The sum from 1 to n of mi, so these exponents, the sum must be 2 to make this a homogeneous polynomial of order 2. And we need that the mi are greater than or equal to 0. And integers, they're integers greater than or equal to 0. What is Si? Si, this is the ith basis element of Rn. So if you want, Si is, there's a bunch of zeros, and then there's a 1 in the ith slot. Okay. So for n equals 2, we have S1 is 1, 0, S2 is 0, 1. Okay. So the basis for H2 on Rn, R2 is this collection, y1 squared, y1 times y2, y2 squared, and then same for the second slot, 0, y1 squared, 0, y2 squared. No, it should be, just to keep the ordering the same, y1, y2, and then y2 squared. So these are, and sometimes we might call this is element P1, P2, P3, P4, P5, P6. There's some formula for, you know, how many basis elements there are, but it's finite. And so you can see, think of it as the vector space of H2 on Rn is spanned by these 6 vectors. So it's a 6-dimensional vector space. All right, so this stuff about the space of vector valued homogeneous polynomials is kind of an aside, but it is good to know and keep in mind. Okay, so back to what we were doing. Here's our ODE written in the form where the linear terms have been simplified. And now we write what we have for x dot, right? We've just rewritten x dot in terms of y dot, and that's what it looks like. Now let's rewrite the right-hand side. What will the right-hand side look like? Well, it'll be j times y. Sorry, j times x. And so that means j times y plus h2y plus f2 of x, but instead of x, it's y plus h2y plus f3 of x, but now it's y plus h2y, and so on. So what does this become? This becomes j times y plus j h2y plus f2y plus, and now we'll write f3 tilde y plus terms of order 4. So what did we do there? Well, since j is just a matrix, it multiplies through. f2 is a second order function, but f2 times h2 is going to be something that's of order, it's going to be of order 3, or possibly order 4. So that's why we modify and move it out. And that modifies f3 and all higher order terms. Okay, now similar to what we did in the 1D motivating example, we need to write this up here. We need to take its inverse so that we'll be left with y dot equals something. So there is a n by n matrix equivalent of the 1 plus epsilon raised to the -1 power. When you have the identity matrix plus a matrix that is small, which we do have because we're assuming we're right next to the origin. So x is small and therefore y is small as well. So this becomes the identity minus, it looks exactly like it does for the scalar case, plus terms of order 2 and higher. I think it's because it's a matrix, it's not called a Taylor series. I think it's called a Neumann series. So then working that out, what do we get? So y dot equals, we'll have identity plus dh2y times jy plus jh2y plus f2y plus f tilde 3y. It's terms of order 4. And then just do the matrix multiplication. jy plus jh2y minus dh2y jy plus f2y plus f3 tilde y, and so on. Now let's group terms. We've got this term, jy is just order 1 in y. What about this term? That's second order in y. dh2y times jy. We're taking the derivative makes dh2 order 1, and then jy is also order 1. So this term is order 2, and then f2y is also order 2. So all of these are order 2. And then we've got, we'll just worry about these later. So those are order 3 and higher. So now we want to pick, we want to eliminate, if possible, these second order terms. So that means, just like we picked the alpha 2 and alpha 3 coefficients in the 1D motivating example, now we want to pick, right, H2 is unknown. So we want to pick H2 such that J H2 Y minus D H2 Y J Y plus F2 Y equals 0. Right, and H2 is it's part of this vector space, capital H2. So this is a linear equation because we're thinking of it in an appropriate vector space, which is H2. So this is a linear equation in the vector space of homogeneous polynomials of order 2 on Rn. It's not clear that we could actually pick an H2 to do this. So we need to examine a map, all right? This is where, yeah, hopefully if you know enough about vector spaces that this will make sense. So we do examine a map, which is you take H2 and then map it into JH2Y minus DH2Y JY. And this is a map, right? This part over here is in capital H2, and so is this part. So this is a map from H2 into H2, and it's linear. And we're going to introduce some notation for this map. It follows Wiggins. We'll write it, and to remind ourselves, linear. L sub J, and we're looking at second order. This is J H2Y minus DH2Y JY. And LJ₂, this is a map that takes in H2. It gives us something on H2. It is linear. So we're using this notation so we could rewrite this kind of simplification equation up here. So simplifying the second order terms involves solving LJ₂, which takes in H2 of Y, equals negative F2 Y. And this is exactly the same as AX equals B, which is a famous, well-known form for solving linear equations. Usually what you do, right, and I guess if you need the analogy taken further, right, here, A is just LJ₂. X is the same as H2Y, right? You could write that as components of a vector space, and here B is the same as negative F2Y. And we could, let me sync this up again. It's not letting me do stuff. Oh no, it erased it all. Okay, so I have to redraw something. That was pretty good too. Right, same as A, X equals B. A is L J₂ X H₂Y. B is negative F₂Y. Okay, we're trying to solve that. It's really easy if this linear map is invertible, this one up here. So if LJ₂ from H2 to H2 is invertible, so this would be like equivalent to does A inverse exist? Doesn't have to, and you could still solve this problem somewhat. Then we can solve for H₂Y. It'd be like writing X equals A inverse B, and there's your answer. But usually this linear map LJ₂ is not invertible. That is, and how do you find out if something is invertible? You look at the matrix representation and see if it's full rank. And if it's not full rank, then we have to do something else. Usually it is not invertible. LJ₂ is not full rank. So we go back to our linear algebra. And what do we know from linear algebra? We know that this vector space can be written, so for any linear map, a non-invertible linear map, this is equal to the image of H2 and then a complement that we'll write as G₂. So this is the image of H2 under the linear map LJ₂. And then this part is the complementary space. It's the part that can't be reached. And we know that F2, the second order terms, are going to be in H2, big H2. So we could write this as, there's the parts that are in the image, and then there's the parts that are not. And these are given names for historical reasons. So this is the image piece. So it's
Is the superscript on the F to the right an N or an R?
It's an R.
Okay.
Because this is I'm not sure why, but it's the resonant piece. And this is the part that is so F2R is the part that's in the complement. F2 image, the part that's in the image of this linear map. So the image piece can be eliminated, but not the resonant piece. And what do I mean by eliminated? You could get rid of those terms by a proper choice of little h2, but not the resonant piece. So this brings up, something interesting that comes up when you have not a 1D equation, but something that's 2D or higher. It's that there could be there's the possibility that there are second order terms that just can't be eliminated. So you can't simplify them away. So H2 can be chosen such that y dot equals jy, so our new equation. We can get rid of everything, all the second order terms except the resonant ones. And then let's just put back our third order terms and then things of fourth order and higher. Okay. And these would be, in some sense, the most simplified. The ones that we can't get rid of, we tried our best. So this is the most simplified order 2 terms. So then one would simplify the third order terms. And there'd be a completely analogous approach. And you can automate this. That's the nice thing about it. Because it reduces to linear algebra, it can be automated. And I think there are codes out there that could do this to any order you want. But let me do an example. Let me see how far we can get through it. Because it's good to see an example. All right. Are there questions before we do the example? Okay. So this is example 19.1.2. And it's in Wiggins. So you can look at it there if you want. All right, so here is our original. It's just 2D. So we'll have a x1 dot and x2 dot. Okay, so this is x2 plus some nonlinear function. And then this is some nonlinear function, g. And this is already in the proper form. So let's just show that. So we got x1 dot, x2 dot written as a matrix times j, where what is j? J here is 0, 1, 0, 0. And then just put things like that. What is H2 for this example? H2 is exactly as I had before. So H2 is the span of y1 squared, 0, y1, y2. Right, we do all the second order terms and in the first slot. That's kind of the convention. And then all the second order terms in the second slot. So this is a 6-dimensional linear space.
In
And
the
yeah,
above
go ahead.
equation, shouldn't there be a vector of variables multiplied by j?
A vector. Oh yeah, there should be. It should be x1, x2. Thanks.
No problem.
And I'll maybe use this notation of calling this P1, this is P2, P3, P4, just as shorthand, P5, P6. You'll see why I want to use this shorthand notation, because what we're going to want to do is, right, LJ₂ times H2 Y1 Y2 equals J H2 Y1 Y2 minus D H2 1 Y2 J Y1 Y2. So we're going to look at the image of LJ₂ by operating on each capital H2 basis element. And I've called these, P sub I. So let me just go through the first one. So if we were to look at LJ₂ of P1, what does that give us? So this would be LJ₂ operating on Y1 squared 0. And what is it? Well, it's J times Y1 squared 0 minus D of, so we need to take the derivative, the Jacobian of this thing times J Y1 Y2. Okay, now plug in, what do we have for J? This is 0, 1, 0, 0 times Y1 squared. What is the Jacobian of this? It's going to be a 2 by 2 matrix, 2, Y1, 0, and then 0, 0. And then again, J, 0, 1, 0, 0, Y1, Y2. Work out all the matrix multiplication. This thing just gives, the first thing just gives us 0. And we'll get something from the second term, which is, we'll get negative 2 Y1 Y2. What do you know? It's another basis element. So it's negative 2 times one of the basis elements. So this means LJ₂ operating on P1 gives us negative 2 P2. So this means we're going to do a matrix representation. So the first column of the matrix representation of LJ₂ is it's going to be 0 and then negative 2, 0, 0, 0, 0. And then we do that for all of the others. Do LJ₂ of P2 equals something. Here's what you're going to get. You're going to get P3, etc. So then I'll just give you what the matrix representation is. It's going to be a 6 by 6 matrix. 0, minus 2, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0. And then a column of all zeros. So we know this thing isn't a full rank. 1, 0, 0, 0, 0, 0. Oh, wait, no, there is a -2 down here. 0, 1, 0, 0, 0, minus 1. And then the final one is 0, 0, 1, 0, 0, 0. My goodness. Okay, so it's a 6 by 6 matrix. Right, because H2 has dimension 6. So we could call this, maybe I won't call it J2, I'll call it A. All right, so this matrix is not full rank. So it has no inverse, right? How do we know it's not full rank? Notice the third column is all zeros. So that knocks that out. Also, if you write P1 as 1, 0, 0, 0, 0, etc., this thing works out to give what we expect. So A times the element P1 equals A times 1, 2, 3, 4, 5, 6. It ends up equaling so -2 P2. And you could do that for all of the others. So since A is not full rank, it is not invertible. We, unfortunately, well, I don't know how you want to say it, just is what it is. You cannot eliminate all the second order terms. Maybe you can get rid of a lot. So silver lining is we can eliminate some. Thus simplifying the second order terms as much as possible. Right, what we're finding is a kind of the second order terms that lead to topological equivalence of the original system. So then what? So I said A is not a full rank. There's A. There are two vectors that are orthogonal to each column in A. So we have to get our linear algebra. 1, 0, 0. This one and this one. It's a 1/2 and that's second to last. So these two vectors are orthogonal to each column in A. So that means they form the basis for the orthogonal complement.
Does that include the 0 column?
No. Wait, what do you mean?
You said that the two vectors are orthogonal toward each column in A, but there's a 0 column.
Yeah, so if you took the dot product, you get 0.
Oh, I see. Makes sense.
So what does this mean? If we translate these column vectors into the what they look like in terms of the homogeneous polynomials, this means we can't eliminate second order terms that are linear combinations of, so this one becomes, if you, so, and now we'll think in terms of the original variables, x1 squared in the second slot, or x1 squared 1/2 x1 x2. So we can eliminate all second order terms except these. By that proper choice of the H2Y polynomial. So I guess we, what are we saying? G2 is the span of these two things. So this means that we can transform from x1, x2 to y1, y2, where in the new equation, what do we have? We've got, this will be y2 plus a2 y1 squared, and then this is a1 y1 squared plus a2 divided by 2 y1 y2, and just leave the third order terms for later. So maybe we had 6 second order terms. Or I guess technically, yeah, technically we would have had 6 second order terms. Now we've eliminated to just these 3 second order terms. Okay. So that would be, that's a simplification. Terms down to 3. I mean, it's 3, but then these two are related by a coefficient that must be kind of common to each. I've written one way to write the span of G2, but this isn't the only one. There are other choices for writing the span of G2. We could also make this choice, which would be x1 squared 0, 0, x1 squared. So the first term squared, in which case this leads to y1 dot, y2 dot equals, this is y2, this is 0. They have different coefficients, so a1 y1 squared plus a2 y1 squared. Let's write it that way. So you have a choice in which ones you eliminate. If you want, where's this mentioned? This is in pages 277 to 278 of Wiggins. And this has a name. This is called the Takens normal form, because it was written up by somebody named Takens in 1974. There's another choice, and I'll kind of end here, which is to write the span of G2. So this one, well, I'll write this other one first. This is x1, x2, and then 0, x1 squared. So these are interesting. It's kind of like, where do you want to put the nonlinearity? Where do you want to put the second order terms? Here, we've got second order terms in each of the directions, but it's the same term. Here, we put all of the second order terms into the second ODE, so that the first ODE is just linear, and then we have third order terms. There's no second order terms. We put all the nonlinearity in the second order, in the second term, the Y2 term. And so this also was given a name by somebody else, Bogdanov. Who wrote this up in 1975. Together, so whichever choice you make, these are taken as the Takens-Bogdanov normal form. And there's a, this gets related to a bifurcation later. There is something else to note. What led to all of this? The choice of whether or not there was a complement or not, whether or not LJ₂ was completely invertible. It all depended on what the linear part was. Here, the linear part was this. So the form of the linear part determines everything. It determines which second order terms can be eliminated or not. And then it also carries on to, it determines which third order terms and so on. So which nonlinear terms can be eliminated is all based on what the simplified linear terms are. So that's kind of interesting. And then you can choose, well, where do you want to put your nonlinearity? Do you want to put your nonlinearities in both of your ODEs, or do you want to push all your nonlinearities into just one of them? And so normal form theory would say that these two systems are topologically equivalent, and they're topologically equivalent to the original ODE that may have had 6 terms. Anyway, we'll stop there. We'll say some more about normal forms. Just like we talked about center manifolds that depend on parameters, next time we'll talk about normal forms for vector fields that depend on parameters, because then that leads to, helps us with studying a bifurcation. In particular, there's a main bifurcation that comes about. It's called the Hopf bifurcation. I think we'll get to that next time. So that is it. Sorry for going over a little bit. Other questions? If not, then I will see you on Thursday.